B3, the slope of a velocity versus time graph. This is going to show us the concept of the acceleration, because if you look at, say, the acceleration as a delta v over delta t, and the same idea for the velocity is a delta x over delta t, that these represent slopes. So if you have, for example, here, the x versus t graph, then the slope here, this would be a change in x. See this change in the height in this geometric picture, and this is delta t. If you take the delta x, which is considered your rise, and divide by your run, then you get the slope. Tells you how high you go up per a step in the right direction. And that is going to give you your velocity. When you have your velocity as a function of time, have something, say, could be something complicated. If you look at a certain place here, and this is delta v going up and delta t, then delta v over delta t is the concept, see, of acceleration, the slope and the velocity and time graph. Now, if you let that delta t slide down to 0, then you get the tangent. See, at that point, that looks pretty good here. See, this is already pretty small, and that's fitting in there pretty well. But if you went to 0, you would get precisely the tangent idea. So let's do that with some numbers. If we look at this graph here, we're looking at the speed in kilometers per hour. Notice that as the time went on, there was a couple drops in the speed, like you shift the gears, you know, drive down a little bit in the speed. A gear shift. I think that's easier to see without the marks on there. So if you look here, yeah, you can see that. Yeah, there you go, right in here. Nice gear shift there. Okay, so if we look at this and want to figure this out for two cases, if we look at this first case, this is at 150 right up there, and this is at 50. This is your height. This is going to be your speeds at the two places, and the run, we're going from 6 seconds to 10 seconds, so that's 4 seconds. So if we look at this, and you want to get the delta v over the delta t, you got to subtract the two velocities. Here's your final velocity, there's your initial. So your rise here is going to be 100 when you subtract, and the run is 4. So when you do that division, you're going to get 25. It's going to come out as 25 kilometers per hour per second. 25 kilometers per hour per second. And if you want to replace the h, you can replace the h, hour, and then you'll get kilometers per second squared. And that will be a small number because you're dividing by 3600, but the same value. And if you want to replace kilometers with meters, in other words, a kilometer is 1,000 meters, you can then convert to meters per second doing that. And we'll just leave it like this, kilometers per hour per second. That means every second you're gaining 25 kilometers per hour. Now, if we look at the second case up in here, we're going, for this particular case, let's say that looks like a 260 up there. And this one here, looks like between 200 and 250. We'll say that's a 225. We're estimating here. And from 17 seconds to 22 seconds, that would be here 5 seconds. So the rise in this case would be, you would take 260 and subtract 225, and that would get you 35. And if you take the rise over the run, you have 35 over 5. So taking the rise over the run, you have 35 over 5, and that's 7 kilometers per hour per second. So that acceleration there, you can see the slope, it's not as steep. So there was more acceleration here at the beginning, and then less acceleration. And then here, when it flattens out, there's no acceleration. You're going at a constant speed. You're not changing your speed. So your kilometers per hour remain the same. Okay, so just a final point is, remember that your acceleration has units, meters per second squared. In other words, there's 2 time units in the denominator. So it could be kilometers per hour per second. It could be meters per hour per second. Say one distant unit up here, distance, and then here, time units. This is a standard one that occurs a lot in homework problems in introductory physics. And this idea of taking the slope is a cool idea. In fact, when you take the slope of the x graph to get the velocity graph, that's called a derivative. You have a derived function. This I drew anyway. I didn't make this one to be related to this graph at all. And if you go to the acceleration plot with respect to time, that would be the derivative or the slope function of the velocity. See, because see, that's your slope here is your acceleration.